Okay, so today we're going to start a new chapter. This chapter, chapter 6, is all about linear transformations. So what I want to do just in this video, give a brief introduction to what they are, and just cover some examples of what you might see on an exam. So I just want to start off thinking way back to Algebra 2. We've done that a couple times in this course. But let's just look at this. F of x is equal to x squared. Very simple equation here. So we can even graph it. Looks like this, something like that. And we can say that we're inputting a number. That number is x, right? Then we end up squaring it, and then what we output is another number. Okay, so but what you'll notice is that, I can input any number, right? I can pick any x value I want. It could be 0, 1, or, 100,000. And I'll always land somewhere on the curve, right? But what you'll notice is that I can't fill every y value, right? I'm not able to go in this area at all because I can't square something to get a negative number, right? So then just the point here is that first of all, this is called your domain, which I'm sure you remember. And then this is called your range. So I want to bring up just these terminologies again from the depths of your brain. And then I also just want to say that the size of the domain in this case is just a little different from the size of the range. So that's just something that I want to keep in mind as we move forward. And to do, actual examples of linear transformations. So what is a linear transformation? Well, it's a way of generalizing the idea of a function. So in calculus, you started learning more and more crazy functions in trigonometry, cosines, and sines. In Math 114, some pretty spooky stuff with 3 and 4 variables in one function. But now what we want to do in algebra is actually generalize the idea of a function to be as general as possible. So now we don't want to necessarily be just inputting numbers, but we want to be able to do something that looks like this. So t of ax squared plus bx plus c, for instance, is equal to a, b, b, and c. Okay, so t I'm just defining to be a function. And I'm inputting a polynomial, right? So I'm no longer just inputting a number like I did in x squared. I'm inputting a polynomial, and then, I'm not outputting a polynomial either. I'm outputting a 2 by 2 symmetric matrix. So how the heck does that work? Well, there's the inspiration here is that there's no reason it shouldn't work, right? There's no reason that I can't give you a polynomial and then tell you to use its coefficients to form this matrix here, right? There's nothing stopping us from doing that. So linear transformations help us do it in a more organized way. The linear part of it should raise not some concerns, but some points in your head about what has to be true of a linear transformation. And so pretty much if we define a linear transformation from one vector space to another, I'm going to draw this out as a picture here. So I'm going to say that this circle here represents my vector space V, and this one over here represents my vector space W. And then I want a way of getting between the two vector spaces. Similarly, like I inputted a number here, and then I outputted a different number over here. I want a way of getting between these two spaces. So I take V1 to be any arbitrary vector in V, and the W1 to be any arbitrary vector in W, and then I define T of V1 that goes between them. Similarly, I can do this for V2. T of V2 will land me somewhere in W, and I'll call it W2. The cool thing about linear transformations is that they have to follow some properties, which we already kind of thought about. So first of all, if I take first my two vectors, I add them together, and then I send them through the linear transformation, it's the same as if I just did it independently through the linear transformation and then added them. Secondly, if I first multiply some element v1 by a scalar k and then send it through the transformation, it's the same as if I just send v1 through the transformation and then multiply it by k. So we've seen these before. These popped up when we were working with proving something's a vector space. These are called the linearity properties. Okay. So before we move forward onto talking about exam problems, this is kind of just our motivation behind studying linear transformations. It's a generalization of a function. That's pretty much all you need to know. Well, no, it's not all you need to know, but for motivation it is. What I want to do now is I want to just talk about kind of a weird parallel that pops up that's important to understand where we go from here. So I'm going to redraw this graph here. So I have a V and a W, and I have some V1 getting sent here to a W1. V is my domain, and W is my range. So my point here is that this is not the first time you've seen me draw this graph. So we actually drew this graph a while ago when we were talking about null space and column space. So if you remember, I defined this little oval here and this oval here. I said that we have some x vectors that live in this oval here and some b vectors that live in this one here. And then to get from x to b, I can define a matrix A such that it multiplies by x and gives me a vector b. So I'm able to take a vector x here, multiply it by some matrix A, and then land in my range over here as B. What's really interesting then is just the parallel between the two of these. So these graphs look almost identical, right? The only difference is that instead of using a matrix here, I'm defining a function. I'm defining a t. So someone said, why the heck shouldn't this t be some sort of matrix? Why can't t be represented exactly in this form over here so that we can kind of keep this parallel going, and because it's working for us? So there's actually a way to define a linear transformation as a matrix, and that's what most of the exam problems will come from. Hopefully that made a little bit of sense to you. It's just, a parallel. You don't really need to know it, but it helps me at least understand what's going on a deeper level. So part of the exam questions you might be asked, as with vector spaces, you might be asked to show that T is indeed a linear transformation. And how do you do that? Well, if a mapping T is a linear transformation, it has to satisfy these, right? So you go ahead and you just, crank those out as you would do normally. And then part two, and this is the more complicated part, is find the matrix A that's associated with this transformation. And this is where things get interesting. This is a really, really cool property of linear algebra, I think. And we're going to go ahead and just do an example problem to get everyone on board with what something like this looks like. So I'm going to define my linear transformation. I'm going to say it goes from R3 into R2. So I'm taking in three-dimensional vectors and I'm outputting two-dimensional vectors. And then it's given by t of x, y, z is equal to x plus y and y plus z. Okay, so notice again that these are different sizes. I'm inputting 3 dimensions and outputting 2. And then, yeah, that's really all there is to it. So let's go ahead and just do this first part here. Let's show t as a linear transformation. Okay, so t must be, or must satisfy the linearity properties. So let's go ahead and define v1 and v2 are elements of R3. So let's let v1 be x1, y1, and z1, and then v2 is equal to x2, y2, and z2. So first I need to say t of v1 plus v2 is equal to t of v1 plus t of v2. And I really wish I had one of those montage things where I can speed this up 10 times, but we'll go through and do it anyway. So t of v1 plus v2 is t of x1 plus x2, y1 plus y2, z1 plus z2, which is equal to, now what I do is I take this x plus 2, and that now becomes this x. I take this y plus 2, this becomes these y's, and then this z plus z in its entirety becomes this z here. So you'll see we'll combine them all together, factor stuff out, and then separate it, as we did with vector spaces. So this is equal to t of x1 plus x2 plus y1 plus y2. That's our first entry here. And then we have y1 plus y2 plus z1 plus z2 is our second entry. This is equal to t of, this is not a necessary step, but I like to do it to be clear. I move stuff around like this. So I put all the 1s up front, all the 2s in the back. x2 plus y2, y1 plus z1 plus y2 plus z2. And this is equal to t of x1 plus y1, comma, y1 plus z1. So I've taken out this and this to be here, and this to be here, because that's how you add 2 coordinates like this, plus t of x2 plus y2 and y2 plus z2, which comes up from the remaining terms here and here. Okay, and then what is this here? This is t of v1. This here is t of v2, and we added them together, so perfect. I'm going to skip the scalar multiplication one because you're pretty familiar on how you do that. And that's pretty much how you would show it's a linear transformation. So I'll put it in here. T of k times v1 is equal to k times t of v1. That's what you'd show. Okay, so for 2 then, we need to find the matrix A that's associated with T. So I'm going to write T again. T goes from R3 to R2, and it's given by T of x, y, z is equal to x plus y, y plus z. And now we need to consult the textbook for a definition. So the matrix A associated with T can be found by this definition here. So if T going from Rn to Rm is a linear transformation, then the M by N matrix A is found the following way. So pretty much I'll write this all out and then I'll explain what it means. T of E1, T of E2, dot, 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 T of E3. Okay, I'm going to circle this so we know it's not part of the problem we're currently working on. Okay, so what does this all mean? So we have this weird E stuff going on. We have a complicated matrix that looks like. But what these E's are, they are the standard basis vectors. And so what that means then, so E1 is equal to a 1 in the first part and zeros everywhere else. E2 similarly is a 1 in the second spot and zeros everywhere else. And then so you can generalize this, EJ is equal to zeros everywhere, a 1 in the jth spot, and zeros everywhere else. This is in the jth spot. So then just in terms of like everyday language, then what we're doing to find A is we're sending through the standard basis vectors. We're sending them through our transformation, and then we're going to put what we get as a column in our matrix here. So let's go ahead and finish up this example here. So we have T of x, y, z is equal to x plus y, y plus z. What I need to do then, I need to find T of E1, right? That's going to be my first column in my matrix A. That's going to be equal to T of 1, 0, 0, because that's just a standard basis vector. And then what I do now is I literally plug in 1 for x and 0 for y and z. So I just get 1, 0. Cool. All right, so then T of E2 is T of 0, 1, 0, which gives me 1, 1. And then T of E3 is T of 0, 0, 1, which gives me 0, 1. So what I do then is I stick these in as columns to my matrix A. So A is going to be equal to 1, 0, 1, 1, 0, 1. And we're done here. So what the purpose of making this this matrix A is so that instead of doing like inputting a vector into T, what I'm able to do instead is I can just multiply this vector A, multiply this matrix A by the vector I want to input, and out pops the vector I would have gotten had I thrown it through the transformation. So there's an easy way to check if this matrix that you found is correct in terms of size. So just as a little life hack here, we know that if we say, T of V is equal to A times V, right? That was what I was saying a little bit earlier. Now we're just multiplying A by this vector V as opposed to inputting it into T. T of V is going to be our output vector, right? That says that our output vector needs to be a two-dimensional vector. So I have a two-dimensional vector here. This is 2 by 1. A, we don't really know the size of it yet. I mean, if we're checking by size. And then V, my vector V is what I'm inputting into this linear transformation, which comes from R3. So V, I know, is going to be a 3 by 1 vector. And how do you get something times 3 by 1 to equal 2 by 1? Well, it has to be equal to 2 by 3. So the 3's will match up here, and then your 2 by 1 will correspond to a 2 by 1 here. Okay, so this is just an easy way to check to make sure you got the size right. And then, yeah, we'll talk a little bit more about what happens in more complicated cases. We'll talk about why there's actually kind of an inherent problem with this definition here, which you may have already picked up on. But yeah, that's all for this video.